All right, so this is from 2017. It's problem number 2. All right, so we have a student that wants to determine the coefficient of static friction between a long flat wood board and a small wood block. Okay, so before we begin the problem, so this problem's focusing on static friction. There are two types of friction. There's what we call static friction, and then the other type of friction is kinetic friction. Now, the equation for both of these, and whether you're doing static or kinetic, the equation for friction is coefficient multiplied by the normal force, where N represents normal force. So if you're dealing with static friction, if you're talking about static friction, then this would be mu static. And if you're talking about kinetic friction, then this would be mu kinetic. Now, the way I explain the difference between static and kinetic is everybody's had the experience of pushing a big, giant block or big old box of some sort. So you come up to this box and you start pushing on the box, and the box is not going to initially start to move, because even though you're applying a force this way, so let's call that force applied, there's a static friction which is opposing. So as this applied force gets bigger, 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 the static friction also becomes bigger, bigger, bigger. So the thing to realize, if you're talking about static friction, you know, where this is static and that's mu static, you know, it's not like static friction can be only one value. So if we graph this, here's what I'm saying. So let's say we look at friction here. So you start to push on the block, right? So you're pushing on the block. This is friction measured in newtons. So you're pushing harder and harder and harder, right? As the applied force gets bigger, 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 the force of static friction gets bigger, 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 until finally you overcome the static friction and you slide down into kinetic friction. So this would be kinetic, the box starts to slide. And generally speaking, kinetic friction is always less than the maximum static friction. So this point right here, this would represent friction static maximum right there. You know, you reach this point where static friction cannot provide any more force to oppose the applied force, and then the object starts to move. So when you plug into this equation here for static friction, you know, if a problem tells you, let's say the problem is like, mu static equals 0.6. If you take that and plug in to this equation, what you're calculating is you're calculating the maximum static friction available. Okay, so let's revert this. Now, part A wants us to describe an experiment for determining the coefficient of static friction. So we want to solve for mu s between the wood board and the wood block. So we need an experiment for doing this. So I'm going to give you guys two options. So here's option number 1. This is what I first thought of. It's actually not what the College Board gave in their answer key, but this would be totally acceptable. So your diagram would look like this. Here's your wood board, and then you have your block. So the block is sitting on top of the wood board, and then you come up to the wood board and you apply, we'll call this force applied, and then it's going to be opposed by a static friction, right? Which is equal to mu static times normal force. Now, this applied force, so for my experimental setup, because we're describing an experimental setup, the applied force, you're going to do it like this. So let me erase this. What you're actually going to do for your diagram, I would just go like this. So that's a free body diagram. So your setup's going to be this. You're going to take a force sensor So let's put a little box right here. So this is going to be a force sensor, just like we have in our physics classroom from Vernier. There's a little hook on there, and then this would be a string. Okay, so what they want us to, so there's our diagram. So we have the board, we have the mass, we attached a string to the force sensor. So we want to draw the diagram, indicate each quantity that would be measured. So we got to measure the mass here, and we need the force. So actually, I would do a second diagram because that's not a free body diagram. So here's the board again. So free body diagram would be mg down. We have normal force up. The force sensor is pulling with a string. So that's going to give us a tension. And then opposing the tension is a static force, which equals mu n. Okay, so now we're going to talk about what we want to record and then the equipment to use it. So we want the quantity that would be measured and what equipment would be used. Okay, so we're going to record. So we'll do record and then the equipment. So we're going to record, number one, we need the mass of the block. And that's going to be m. And then the equipment for doing that, you would just say a balance. A balance, or you could specify electronic balance. Most classrooms have an electronic balance. Okay, second thing we're going to record is the reading. We want to record the reading of the force sensor at the moment the block begins to slip. At the moment block slips and starts to move. So to do that, we're going to use the force sensor. So this would pretty much nail this part right here. Now, for your procedure, so I'm not going to write this all down. I'm recording this, so if you want to go back and watch the video. Oh, by the way, all these videos are now posted on YouTube. So I'm just going to write out a procedure. Well, I'm sorry, I'm going to say the procedure as I number it. So number one, you're gonna say this: place block on the horizontal wood board. So block goes on horizontal wood board. Then step two, attach the force sensor to the block with a string. Attach force sensor to the block with a string. That would be step two. Step three, you'd write begin to pull on the block and gradually increase the applied force. So you want to increase the tension that's acting on the block. And again, as tension gets bigger, the force static will get bigger as well until you reach the maximum force, the maximum amount of static friction. So step three was begin to pull on block and gradually increase the applied force. Step four, you could say record the reading of the force sensor at the moment the block begins to slip. As soon as the block begins to slip, you know that you've reached the maximum static friction. So that's the reading you want to record from the force sensor. And then step five, and this is hugely important, is to repeat this several times. Repeat this procedure several times. And in fact, that's what they're getting at right here when they say include any steps necessary to reduce experimental uncertainty. Pretty much the answer to this is going to be multiple trials. They want that. Mention multiple trials. So that would be our step five. Okay, so that's option one. Actually, let's go ahead and do part B for option one. So let's shrink this down. Okay, so moving on to part B for option one, derive an equation for the coefficient of static friction, which is mu s, in terms of the quantities measured in the procedure from above. Okay, so to do this, we're going to start with this free body diagram right here. So starting with the free body diagram, assuming that this is x and this is y. So part B, you're going to sum forces x, which is going to be tension minus mu normal. So we have tension pointing positive. We have mu normal pointing negative. Those are the only two forces in the x direction. Sum of the forces always equals ma. This acceleration is 0 because we're focusing on the block when it's on the verge of slipping. You know, if we pull any harder, if tension gets any bigger, the block will accelerate, but it's on the verge of slipping. So sum of the forces here goes to 0. And then we're going to sum forces in the y direction. So that's going to be normal force minus mg equals ma in the mass times y acceleration. But looking at this block in the y direction, there is no acceleration vertically. So that goes to 0 as well. And what we're going to do, oh, and this is going to be mu s, that's mu static. We're going to combine these two equations. So normal force must be equal to mg. Take that, plug it in up there. We get mu equals tension over mg. And all of these can be measured. Tension was the reading of the force sensor, and then mass was, oh, you know what we didn't do? In my procedure, let's put step 0. I forgot to say a step. Step 0 should be measure the mass of the block. That should be in our procedure, but it's definitely measurable. All right, so that would be option 1. Now really quickly, I want to do, there's a second option here. Option number 2, what you could do is your diagram would look like this. You're gonna take your board and you're going to put it at an angle, measured theta. And then here's the block on the board, like that. And then what are we gonna record? So we're back to here. So we're drawing a diagram. Include what quantities would be measured. So we're gonna need to measure the mass of the board and theta. So we're gonna record, and then the equipment. So we're answering this question right here. So we're going to record the mass of the block, which actually is going to cancel, but you would not be penalized for saying to record mass of block. I would put it down. It will cancel mass of block, and we'll use the balance. And then we need to measure angle of incline as block begins to slide. At the moment the block begins to slide. Angle of incline as block begins to slide, right? So theta here is going to get bigger, bigger, bigger until there's not enough static friction to keep the block in place, and then it will begin to slide. The equipment for that, you could just put protractor. Measure the angle of the incline using a protractor. Okay, now for our procedure. So again, I'm just going to say the steps, and you can write them down if you want. So step number 1, you could say measure mass of the block. And like I said, mass will cancel when we get to part B here, but they're not going to penalize you for taking the mass of the block. Okay, so place block on horizontal board. So with the board being horizontal, you know, before this board has been elevated, I'd say place block on the horizontal board. Step number 2, gradually increase the angle of the board. So we're going to gradually start to increase the angle at which the board, between the board and the horizontal surface. And then step 3, record using a protractor, the angle of the incline when the block begins to slide. Record using a protractor the angle of the board when the block begins to slide. And then step 4, and this is about reducing uncertainty. We want to reduce experimental uncertainty. You're going to say repeat multiple times. That will reduce your uncertainty. Okay, then deriving an equation. So this is a good review of how to do incline problems. So I'm going to take this, I'm going to do a free body diagram for our situation. So we're deriving an equation for the coefficient of static friction. So here's the incline. In fact, let me make that a little steeper. So here's our incline. The incline is at an angle theta. Here's our mass on the incline. The forces acting on the mass are mg down. We have normal force, which is always perpendicular to the surface. And then friction is keeping the block from moving until there's not enough static friction to prevent it from sliding. And then friction static, that equals mu static times normal force. Now, for dealing with incline problems, to greatly simplify things, to simplify this, we're going to make the incline the x-axis, and we're going to make perpendicular to that the y, right? This is going to make life much easier. So let's sum forces x and sum forces y. So in the x direction, we have two forces. The incline is the x direction here. We have two forces. So obviously, friction points perfectly x, and then the other x force is the x component of mg. So this right here represents mgy. This is mgx. This would be theta. So the two x forces, we have mgx pointing down the incline and friction pointing up the incline. Let's say that down the incline is plus and up the incline is minus. So the x component for mg is going to be sine theta mg, that's this guy, then minus static friction, which is mu static times normal force. Sum of the forces equals ma, but again, this is we're looking at the block when it's on the verge of slipping. In the x direction, acceleration is 0. It's on the verge of slipping. Now go to the y direction. In the y direction, we have two forces. We have normal force, and we have the y component of mg. So let's say that up is plus and down is minus. So summing forces y, we're going to get normal force minus cosine theta mg equals 0, because the forces cancel. And now we can combine these two equations. So we're solving for mu static. So let's take this y equation. Normal force is going to be cosine theta mg. Plug that in right here for normal force. So what we're going to get is this. Doing the algebra, mu static is going to be sine theta mg over the normal force, but the normal force is cosine theta mg. So we're going to plug that in. So this is going to be cosine theta mg. Mg's cancel. Sine over cosine is tangent. So you could just say that mu static equals tangent theta. So I gave you two options there. I know that was a little bit time consuming, but I think that was a good review. All right, so let's go on to the next part. So now we have a physics class with 6 lab groups, and here are the results of the 6 groups. Let's just skip here to part C. So the data that they've collected is summarized. Coefficient of kinetic friction and coefficient of static friction. Based on these data, what conclusion should the students make about the hypothesis that the coefficients of static and kinetic friction are equal? So what they did is, you know, these 6 lab groups, they added up their results and got an average. And these averages came out the same. So this lab group is looking at this and they're going, huh, the coefficient of kinetic is equal to the coefficient of static, which we know is absolutely not true. As I said before, we all know from being alive, objects, the way it works, you come up, you start pushing on this box, you're gonna push, to overcome the static friction. Once you have overcome the static friction, you drop into kinetic friction, right? So this is maximum static right there. Static friction will always be bigger than kinetic friction. Now, why is this data misleading? The reason it's misleading is group number 5 has an outlier. So notice for all these other groups, we have a small kinetic with a bigger static. And that's true for all of them. Small kinetic, bigger static. All the way down, that's the case. And then we get to group number 5, which has a ridiculously big kinetic with a ridiculously small static. So this is what you call an outlier. You know, it doesn't agree with the rest of the data. So we would say the static and kinetic coefficients are not equal. In justifying your reasoning, you're going to talk about how group number 5 has an outlier. Once that outlier is removed, we will see that, yes, in fact, kinetic friction is smaller than static friction. Okay. And then D, last question, a metal disc is glued to the top of the wood block. Okay, so we have, here's the board, here's the block. So we're gluing on another object on top of the wood block, essentially making the mass of the block bigger. Does the coefficient of static friction between the bottom of the block and the board increase, decrease, or remain the same? Okay, the way friction works, the coefficient, when you talk about the coefficient between 2 objects, what that is it's a measure of how these physical materials interact with each other. You know, is the board made of wood or is the board made of plastic? Because a wood block is going to interact differently with a plastic board compared to a wood board. So this coefficient is not dependent upon the weight of this block. It's dependent upon how these materials interact with each other. And in fact, if you look at option 2, which I've already erased, but the situation where we had the mass on the incline, when we solved for the coefficient, mass dropped out completely, and we got mu equals tan theta. Mass didn't matter at all. And even for option 1 is where we had the horizontal surface and we hooked up the force sensor. The equation we got there, so this was the force sensor. We pulled on this block until it started to slip, and the equation we came up with for coefficient was the tension in the string divided by mg. So this could be a little bit misleading because you're like, oh, mass does affect coefficient, but in fact that's not true, because if you think about it, if the mass of this object got bigger, you would now need a larger force to overcome the static friction, simply because the normal force is larger. So at the end of the day, mass is still irrelevant.